Introduction. Students, today we will study a new topic. Before further proceeding, I want to ask you something. Do you know about this? Sir, it's a resistor. No, Ram, it's not a resistor. Anybody else? Okay, I will tell you. This is a capacitor. It is used to store the electric energy. Now, I am taking two capacitors of 5 microfarad and making combinations from these. The equivalent capacitance value in this case is 2.5 microfarad. The equivalent capacitance value in this case is 10 microfarad. Sir, how the value of equivalent capacitance change by making changes in their combination? Good question, Ajay. Let me tell you. In series combination, the reciprocal of the equivalent capacitance is equal to the sum of the reciprocals of the individual capacitances. However, in parallel combination, the equivalent capacitance is equal to the sum of the individual capacitances. Students, today we will study more about this in chapter Electrostatic Potential and Capacitance. Objectives. At the end of this lesson, you will be able to define dielectrics, understand polarization in dielectrics, explain capacitors and capacitance, describe the parallel plate capacitor, analyze effect of dielectric on capacitance, know about combination of capacitors, calculate energy stored in a capacitor, understand Van de Graaff generator. Dielectrics. A dielectric is an insulating material like mica, glass, or ceramic. Dielectric materials are of two types: polar and non-polar. Polar dielectric. Polar materials are composed of molecules that have permanent electric dipole moments. In a polar dielectric, the molecular dipoles are randomly oriented when no electric field is present. When an electric field is present, these dipoles experience a torque and tend to align with the electric field. Non-polar dielectric. Non-polar materials contain molecules that do not have permanent dipole moments. When a dielectric consisting of non-polar molecules are placed in an external electric field, the positive and negative charges of the molecule experience forces in opposite directions and become displaced relative to each other. The molecules are said to become polarized by the field and are called induced dipoles. Polarization in dielectrics. The extent to which the molecules of a dielectric become polarized by an electric field or oriented in the direction of the field is described by a vector quantity called the electric polarization. P is equal to Np, where N is equal to molecules per unit volume. P is equal to dipole moment of each molecule. For linear isotropic dielectrics, P is equal to product of Xi and E, where Xi is known as electric susceptibility of the dielectric. The positive ends of the dipoles remain unneutralized at the right surface and the negative ends at the left surface. The unbalanced charges are the induced charges due to the external field. The polarized dielectric is equivalent to two charged surfaces with induced surface charge densities positive sigma p and negative sigma p. Capacitors and capacitance. Capacitor. It is a device that consists of two conductors isolated from each other so that they can be given equal but opposite charges. Because of the charges minus Q and plus Q, the electric potential of the positive conductor exceeds that of the negative conductor by an amount V. The magnitude Q of the charge on each conductor is proportional to the potential difference V between them. Q is directly proportional to V, or Q is equal to CV. The proportionality constant C is called the capacitance of the capacitor. C is equal to Q by V. Capacitance. It is defined as the ratio of the magnitude of the charge on either conductor to the magnitude of the potential difference between them. The SI unit of capacitance is coulomb per volt, called farad. Capacitance of a spherical conductor. Let us consider a conductor in spherical shape of radius r. If this conductor is given a charge Q, the potential at its surface is given by V is equal to 1 upon 4 pi epsilon not multiplied by Q upon R. It can be written as Q is equal to product of 4 pi epsilon not R and V. We know that Q is equal to CV. On comparing above equations, the capacitance of the spherical conductor is given by C is equal to 4 pi epsilon not R. This relation shows that the capacitance of spherical conductor is directly proportional to its radius. Larger is the radius, larger will be its capacitance. This expression is true for the conductor placed in air or vacuum. If the conductor is placed in an insulating medium with dielectric constant K, then the potential at its surface is given by V is equal to 1 upon 4 pi epsilon not K multiplied by Q upon R. It can also be written as Q is equal to product of 4 pi epsilon not K, R and V. Thus, C is equal to 4 pi epsilon not Kr. Hence, the capacitance of the conductor in the dielectric medium is K times its capacitance in air or vacuum. The parallel plate capacitor. A parallel plate capacitor consists of two parallel conducting plates separated by a distance that is small compared with the linear dimensions of the plates. Let the plates are in vacuum. If sigma is the magnitude of surface charge density on either plate, the electric field magnitude between the closely spaced parallel plates is equal to sigma upon epsilon naught, but sigma is equal to Q by A. Put the value of sigma in the above equation. We get E is equal to Q divided by epsilon naught A. Here, A is the area of each plate. The electric field between the plates is uniform and the potential difference between the plates is given by ED, which is equal to QD upon epsilon naught A. Here, D is the distance of separation of plates. The capacitance of a parallel plate capacitor is equal to Q upon V, which is equal to epsilon naught A upon D. Thus, we conclude that the capacitance of a parallel plate capacitor in vacuum is directly proportional to the area of one of the plates, inversely proportional to the separation of the plates, and independent of the charge on the capacitor. Effect of dielectric on capacitance. Consider a parallel plate capacitor having dielectric slab between capacitor plates. We consider A is equal to area of each plate, D is equal to plate separation, T is equal to thickness of dielectric slab, K is equal to dielectric constant of the dielectric, sigma is equal to magnitude of surface charge density of the plates. Electric field between the capacitor plates but outside the dielectric is given by E naught is equal to sigma upon epsilon naught. Electric field within the dielectric medium is given by E is equal to sigma upon product of epsilon naught and K. Potential difference between the capacitor plates is given by V is equal to sigma upon epsilon naught multiplied by D minus T plus T upon K. Capacitance is given by C is equal to A epsilon naught divided by D minus T plus T upon K. When dielectric medium fills the entire space between the capacitor plates, then T is equal to D. It gives C is equal to Kc naught, where C naught is the capacitance in vacuum. K is equal to C upon C naught. The dielectric constant of a dielectric is the factor by which the capacitance of a capacitor increases from its vacuum value when the dielectric fills the entire space between the plates of the capacitor. Dielectric constant of the conductor. Let us consider an external uniform electric field E between two charged capacitor plates. Now a conducting slab is introduced in the field. The free electrons of metal are attracted towards the positive plate of E, and thus negative charges minus Q resides on the outer surface of metal slab that faces the positive plate of capacitor. Equal amount of charge plus Q will go on the outer surface of conductor that faces negative capacitor plate. Thus, outside the conductor slab the field remains E. Inside the conductor slab, a field EI is induced, equal in magnitude of E but opposite in direction. Thus, net resultant field inside the conducting slab ER is 0. It gives E upon ER is equal to K, which is equal to infinity. Hence, the dielectric constant of metal is infinite. Combination of capacitors. Two or more capacitors may be connected to each other in certain combination to produce an equivalent capacitance of any desired value. the equivalent capacitance C of a combination of capacitors is defined as the capacitance of a single capacitor for which the charge is the same as for the combination, when the potential difference V is the same. There are two types of combinations as follows: capacitors in series and capacitors in parallel. Combination of capacitors in series. In a series circuit, each capacitor gets the same charge as delivered by the battery, while the total EMF of the battery is distributed across different capacitors in inverse proportion to their capacitances. The reciprocal of the equivalent capacitance is equal to the sum of the reciprocals of the individual capacitances. 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 by C3 plus so on. The equivalent capacitance is always less than the smallest capacitance in the series. Combination of capacitors in parallel. In a parallel circuit, each capacitor gets the same potential difference equal to the EMF of the battery, while the total charge drawn out of battery is distributed in different capacitors in proportion to their capacitances. The equivalent capacitance is equal to the sum of the individual capacitances. C is equal to C1 plus C2 plus C3 plus so on. The equivalent capacitance is always larger than the largest capacitance in the parallel combination. Example on combination capacitors. Let's take an example on combination of capacitors. A technician has only two capacitors. By using these capacitors singly, in series or in parallel, he is able to obtain the capacitance of 4, 5, 20 and 25 picofarad. What are the capacitances of the two capacitors? Let's see the solution. We know that the resultant capacitance is maximum in parallel grouping. Cp is equal to C1 plus C2, or Cp is equal to 25 picofarad. Also, the resultant capacitance is minimum in series grouping. Reciprocal of Cs is equal to 1 upon C1 plus 1 upon C2, or Cs is equal to 4 picofarad. Thus, the maximum and minimum values are 25 picofarad and 4 picofarad respectively. Remaining values 20 picofarad and 5 picofarad represents the individual values of the two capacitors. Difference between series and parallel combination. In series combination, negative plate of one capacitor is connected to positive plate of the other and so on. Whereas in parallel combination, positive plates of all the capacitors are connected to one common terminal and negative plates are connected to another common terminal. In series combination, charge on each capacitor is same. Whereas in parallel combination, potential different across each capacitor is same. In series combination, V is equal to V1 plus V2 plus V3. Whereas in parallel combination, Q is equal to Q1 plus Q2 plus Q3. In series combination, reciprocal of CS is equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3. Whereas in parallel combination, CP is equal to C1 plus C2 plus C3. In series combination, capacitors are connected in series to decrease the capacitance. Whereas in parallel combination, the capacitors are connected in parallel to increase the capacitance. Energy stored in a capacitor. The process of charging a capacitor consists of transferring charge from the plate at lower potential to the plate at higher potential. The work done in the charging process is stored as potential energy of the capacitor. At charging process, the potential difference between the plate is V is equal to Q by C. The additional work dW needed to transfer the next increment dQ of charge is given by dW is equal to V dQ, which is equal to Q by C into dQ. The total work required to charge the capacitor from its initial value 0 to a final value Q is given by integration of dW. Put the values of dW in the equation. We get W is equal to 1 upon C integration from 0 to Q of Q dQ, which equals to Q square upon 2C. Thus, the energy stored in the capacitor is given by U is equal to 1 by 2 CV square. Van de Graaff generator. A Van de Graaff generator is an electrostatic generator which uses a moving belt to accumulate very high voltages on a hollow metal globe on the top of the stand. The potential difference achieved in it can reach 5 megavolts. Principle: when a positively charged conductor is connected internally with a hollow conductor, the whole of its charge flows to the outer conductor. Potential difference between the spheres is given by VR minus VR is equal to Q upon 4 pi epsilon naught multiplied by 1 by R minus 1 by R. Working of Van de Graaff generator. The insulating belt is wound around two pulleys, one at ground level, one at the center of the large spherical conducting shell. This belt is kept continuously moving by a motor driving the lower pulley. It continuously carries positive charge sprayed onto it by a metal comb at the ground level to the top. There it transfers its positive charge to another metal comb connected to the large shell. Thus, positive charge is transferred to the shell, where it spreads out uniformly on the outer surface. An iron source placed inside the shell is at a high potential relative to ground. Therefore, charged particles can be accelerated to high energies along a tube to collide with a target for various experiments. Did you know? Because of the ability of the capacitor to block current flow, it is often used as a filter. An interesting demonstration with the Van de Graaff is to make someone's hair stand on the end. Dielectric mirror is composed of multiple thin layers of dielectric material, typically deposited on the substrate of glass or some other optical material. Summary. Let us summarize what we have learned. Polar materials are composed of molecules that have permanent electric dipole moments. Non-polar materials contain molecules that do not have permanent dipole moments. The extent to which the molecules of a dielectric become polarized by an electric field is described by a vector quantity called the electric polarization. Capacitor is a device that consists of two conductors isolated from each other so that they can be given equal but opposite charges. Capacitance is defined as the ratio of the magnitude of charge on either conductor to the magnitude of the potential difference between them. The dielectric constant of a dielectric is the factor by which the capacitance of a capacitor increases from its vacuum value when the dielectric fills the entire space between the plates of the capacitor. When a positively charged conductor is connected internally with a hollow conductor, the whole of its charge flows to the outer conductor.